Okie dokie. So, hello. We're going to start off where we ended last session, but I will actually let you guys vote. Do you want to first do some more Chapter 17 questions and then go back to these practice problems, or do you want to finish these first and then go back? So 17 or practice problems first. What do you guys think? Okay, so one person said don't have a preference, and then a couple people said practice problems, so let's just go ahead and do that first. All right. So actually we did go and skip a couple of these in the exam review that I did, so let me just make sure we haven't skipped any. Did that one. Okay, so let's start over here. So this is one of my favorite questions for this section. And the question is, which of the following is going to give products in a substantial amount? So that's kind of the tricky part here. So it's basically which one is going to make real product, right? And the first thing we have to notice is what kind of reactions each one is. So we have an alkyl halide and AlCl3. So what kind of reaction is that? Friedel-Crafts. Alkylation, cool. And so all of these are actually Friedel-Crafts, so I'll go like this. Cool. And so we see that it's Friedel-Crafts alkylation, and there's NH2 on the ring. Can that happen with NH2 on the ring? No, correct. So NH2 is not a strong deactivator. However, Friedel-Crafts cannot happen. So I'm going to go ahead and circle. No. Reaction. No. Reaction. So these two must be wrong, right? But what about this one? This is where people get tripped up. So let's draw out CH3, CH2, CH2, Cl, and we get this product. Do you think this will produce this product? Okay, I got one yes. Ooh, I got a no. I got another no. Ooh, why not? Why no? Oh, someone backed out. That's okay. All right, so the correct answer is no. This is not going to proceed this way. And the reason is, in a Friedel-Crafts alkylation, we get a carbocation. Yes, and we get a rearrangement. So this is not the most stable carbocation. This is, we did a hydride shift. And so this is what's added to the benzene ring. So our actual product would have been benzene with this group on it. So this would have been the major product, not this one. So for that reason, the answer here is E, none of the above. It's a tricky one, but it's not necessarily difficult. Okay, so someone asked, how do I move the charge? So we had the plus here, which means we only have 2 hydrogens, and we have 2 here. So what we're going to do is take one of these hydrogens and move it there. So you end up with H, 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 and a plus charge. So that's a hydride shift. Good question. And it went from primary to secondary. Make sense so far? I noticed someone just popped in, so I'll give them a moment to take a picture of this or anything. Oh, 2 people just popped in. Cool. Okay. And again, I can always go back at the end if you so need. All right, this is another one that I really like. So we have 2 benzene rings this time, and we flipped around the arrow. So we have our acid here and our alkyl halide here. So what kind of reaction is this going to be? Friedel-Crafts. And it's going to be an alkylation. Perfect. And the reason we knew it was Friedel-Crafts alkylation, 1, AlCl3 always means Friedel-Crafts. And if we have an alkyl halide, that means it has to be an, alkylation. That was a loud hiccup. So, rules of Friedel-Crafts. They cannot happen with a strong deactivator or with NH2. So, we have 2 rings in this example. We have ring A and we have ring B. Does ring A have an activator or a deactivator on it? Yes, it has a strong deactivator because this group is a strong deactivator. It has a carbonyl. But how about ring B? What does ring B have on it? An HN, exactly. And so directly attached, it has, a lone pair of electrons, which makes this, an activator. So, Friedel-Crafts cannot happen on this ring, but it can happen on ring B. Next step, we know that it's an ortho-para activator, so we can add the group here, here, or here. And so when we look at the answer choices, and someone said, so you basically split the director? Yeah, kind of. So this is one functional group, right? So I don't want you to think like, oh, it's always going to count as multiple functional groups. No, it's just one. However, we're going based on what exactly each ring is directly attached to. So for this one, we could split it into 2 pieces because we know that esters and amides, depending on which side it's attached to, have different effects, So when we look at the answer choices, this is the Rosemary way to go through it. So why is this on ring A trash, garbage? Why is it on ring A trash, garbage? Why is it on ring A trash, garbage? For 4 and 5, they're on the right ring. This one is para, this one is meta. He can't get you with this trash, trash, trash. So the only answer that's possible is E. Ta-da! Okay, so just to reiterate, ring A was crossed out because Friedel-Crafts cannot happen with a strong deactivator, and ring A is attached to a carbonyl, which means it's a strong deactivator. So this ring cannot do Friedel-Crafts. So for that reason, 1, 2, and 3 can be immediately crossed out. You're very welcome. Alrighty, so let's go to the next one. Alright, so there's 2 separate ones on this page, and I hope you guys can tell that they're 2 separate ones, but I'll do a little red line just in case. Okay. So it's another 2-ring thing. And now we are doing Br2 and FeBr3. So this is a bromination. So we are adding a Br. And now we're going to figure out where we could add this Br, right? So this one is slightly different because it's not Friedel-Crafts, so you can't just cross one side out. But if we were to use ring A versus ring B, we're going to get some different answers, right? So let's just do ring A in purple. So this we said is a strong deactivator, and it's meta directing. So meta would be here and here. And then we know that this CH2 is not going to be like the nitrogen, right? It doesn't have a lone pair. So it's not like super, super activating or anything. It's a very, very weak activator. But we're still going to say it's an activator because it's an R group. And it's going to be ortho-para directing. So it would be here, here, and here. And so of our answer choices, we can immediately cross out this one because that's para, trash. We can also cross out this one because that's ortho, trash, right? And so which answer do you think it will be? Without any further information. Okay, so someone said number 4, which would be D. Does anyone agree, disagree? All right, let's do an unveiling. You are correct. So the answer would be D. And the reason for this is the predominant product would be the most favorable one. And so between these two, you would rather, You would rather be directed by the most activating group. So even though it's a super weak activator, that's going to beat a strong deactivator. So B is going to direct, and it ends up being para. Any questions on that one? All right, so let's zoom in and do this one. So now we have 2 things on, oopsie. So it won't be a mixture, it's just going to be number 4. And the reason for that is kind of like the ones like this. If we're choosing a director between the strong deactivator and the weak activator is going to have the preference. So for that reason, we only make this product and not both. Alrighty. So for this one, it's a bromination again, so we're going to add a bromine. And let's look at our two options. We have NO2, that is a strong deactivator, meta-director. What about SO3H? So it is a deactivator, and it is meta, so is it strong or weak? Strong. Remember, the only weak deactivators are the halogens. All right, so they're both strong deactivators. Which one is going to do the directing? If you don't have it memorized, that's okay. You can just look at the table. Yes, so SO3H is the weaker deactivator, and I'll show you what I mean. Oh, that's chapter 15. Sorry. Okay, here we go. So much. I'm so sorry. I thought I knew where that was. Okay, cool. So if you use this as your kind of director guide, you can see that SO3H is less deactivating than NO2. So we know that this is the director. And someone made a good point. So in this case, both of them have a meta position here, right? So for this example, you didn't actually need to know which one was stronger and weaker, but I wanted you to do it for practice. But I'm really, really glad you saw that and you pointed it out. So the answer is going to be when it's added here. So when we're looking at this, even if you know nothing, you will remember that I told you you cannot add something in the middle of two groups. That is so cramped. Would you, if the school bus was empty, would you cram 3 people in one seat? No, you wouldn't, because that's annoying. So, ew, trash, garbage. Hate it. Now, we have these 3 options, which if you get it wrong and you pick one of these, I'll kind of respect it, right? But whichever one you chose, NO2 or SO3H, this is orthopara, this is orthopara. Strong deactivators never do orthopara, so this is your answer. And let's just make sure we are correct. We are correct. Yay. Any questions about these two? Okay, if not, we shall move on. Okay, so I want you to get really good at looking at these and knowing what reaction it is. So every time you see a question, you're going to find a defining characteristic. Someone already said Wittig, and you are correct. So if you see PH3, and let me remind you, phenyl equals C6H5 equals well, I don't want to. Okay, let's just say there's something there. So all 3 of those things are equal. So here we have a PPH3, and we have this guy. So when we see those 2 things, we know we're making the Wittig. So let's look at our actual first reagent. So we have this guy. So PPH3 and base is going to turn this into this. So this is G. And now this guy is reacting with this guy. So we're just cutting off the arms and legs, right? So we bam, bam. O and pH are going to go have fun. We don't really care. But we do care about, excuse me, is what happens to the Wittig side. So this is the side from our ketone, and it's double bonded to the side with the Wittig reagent. Sorry, the way I drew it is not cohesive. Ta-da. Okay. All right. So remember, we can mix and match these two, and we can mix and match these two, but we can never flip-flop this way. That's not going to happen. So I swear I am in here, room. You don't have to keep turning the light off. Come on. It hates me. Whatever. So let's find which answer choice matches here. First of all, this one has a double bonded oxygen. What the heck? Trash. Double bonded oxygen, trash. So we've already gotten rid of two choices, right? This one doesn't have, before I say something, let me just make sure. Yeah, this one does not have a double bond whatsoever. Trash, where's the double bond, right? So now you're stuck with D and E. Now I want you guys to take a look at it for a second and tell me between D and E, which one you think looks more correct. And while you're thinking about that, I'm going to go ahead and draw out these answer choices, just so you guys can get a visual. Thank you so much, Light. Okay, someone said I'm lost, so we can definitely go back and review it. But let's just draw out these answer choices. Awkward silences are so uncomfortable. Ba-dum. Okay. So nobody else gave an answer, so I am getting the feeling that everyone's a little bit lost. So let's just go ahead and erase all this. And let's look at this one more time. So whenever we see these two steps consecutively, we know that we're making the Wittig reagent. So in these two steps, we're making the Wittig reagent, aka halide. That's what's happening here. And so in step number 1, we go from this alkyl halide and we react it with PPH3. And remember, PPH3 is just going to kick this off and replace it. So we end up with PPH3. And we have a plus sign here. And we know we have a hydrogen available here. And so the next thing that's going to happen before I show you the next step, this is F. So F is this right here. And so from F, we react it with this. And so this is a strong base. And it's going to come over here, steal a proton, and give those electrons to the carbon. So we get the benzene never changes. Well, not never, but in this example, it doesn't change. So now we get one hydrogen left. We got P, pH3, and we made a double bond with the electrons from the red hydrogen. So at this point, we have G, aka the ylid. Yay. So this product right here is G. And so now G is going to act as a reagent, and we're going to take this guy right here, and I'm going to redraw him down here. He looks like so, the lovely ketone. And we're going to react it with the ylid that we just made. And now we're going to do this the rosemary way. So in the rosemary method, we are going to cut off the heads, and we get O double bonded to P, P, pH3. Cool. And the more important product, I love that I didn't even draw an arrow. Okay, never mind. Good enough. So we get the side product, and the main product is just the arms, aka this, plus the legs, aka, okay, I messed up. Ta-da. So this is our main products. The reason I drew it in this orientation is because two benzene rings are very big. I don't want to draw them next to each other. But again, these two can swap places, but these two cannot. Or, excuse me, these two can... Let me just show you what I mean. So this can swap places with this, but this cannot swap places with this. I'm so sorry if that last part was confusing. My brain just left my body for a second. All right, so now that we did all this, let's look at the answer choices. Clearly, some of these are dumb. We don't have a double bond to oxygen. We don't have a double bond to oxygen. So these two are automatic garbage. And so these are a little confusing. So this was B, this was C. And for A, we don't have any double bonds at all, and we have this OH. Where the heck did we get that from? I don't know, trash. So you're stuck between D and E, which both look pretty similar to what we did, right? Looking at all of this, which one is correct? D or E? Only one person gave an answer. So I'm going to awkwardly sit here until someone guesses or tells me that they're lost. La-di-da-di-da. La-di-da-di-da. Okay, cool. Thank you very much. So a couple people said E, a couple people said D, and I purposely drew it this way to trick you a little bit. I'm so sorry. So E is the correct answer because we're looking for the answer that has a methyl, two benzenes, and a hydrogen. E has a methyl, two benzenes, and a hydrogen. It's just attached differently than I drew it. This one is exactly how I drew it, except it doesn't have a methyl, it has a hydrogen. So be very careful of those little tiny things that can trip you up. Someone said, well played. Thank you. All right, so I'll leave this up for a second. I know that was a big one. Okay. We did this one. We did this one. So let's go here. Alrighty. So, oh wait, I will wait. Did you want to go back and do this one again? Because I feel like this one was hard this morning. No picture. Okay, cool. Go back. Okay, cool. So I will be a deer and draw this out for you, but first I want you to tell me, what functional group is this? Ooh, okay. It is a carboxylic acid, and this is one of those ones that trips people up, but you gotta know it because it'll save you a lot of time on the exam. So COOH equals this. Okay, COCH3 equals this. People always get tripped up on that. And then if you see COH, excuse me, you have this. And that should be it. So just know those, they're useful, they save you a lot of time on the exam. So let's draw this guy out. All right, so this is reacting with PCl5, CH6, C6H6, excuse me, and NABH4. That's a lot going on. So let's break it up piece by piece. PCl5, what's that going to do? And you don't have to give me a big complicated answer, just whatever you think. It could be protecting. This is definitely a protecting group. But whenever we have an OH, these guys are going to swap OH for a halogen. So that's what it's going to do. So we're going to swap the OH for a halogen. And And so now we have this, and we have this guy. So what's C6H6? Benzene, yes. So we're gonna react with benzene and AlCl3. So what is AlCl3 telling us immediately? What kind of reaction is this? Friedel-Crafts, cool. And we don't have an, oh, I didn't even know to ask. Yes, it's an acylation because we have the double bond here. So this is an acid halide. So we know it's a Friedel-Crafts acylation. So all we do is add the benzene group, and we're just gonna cut this guy out and attach directly to the double bond. All right, so at this point, we have D. And let me just label so nobody gets confused. So from here, we have one last step. What does NaBH4 possibly do? Let's zoom out just so you can see the whole thing. Someone said something, but I don't really understand what it means. Reduction. Cool. So if we go ahead and reduce this, yeah, H minus, it's gonna pew. And we get, I'm just gonna draw this in all black right now because it's too many colors going on. O, H, and what do we think is gonna happen next? Intramolecular something. Okay, so at this point, I think it's pretty safe to look at the answer choices for a second. No matter what we do at this point, we're not getting this, right? Because we can't get rid of a carbon-carbon bond. So this is automatically garbage. And for this one, how did we move around those carbons, right? How did we make it in that orientation? So this one is also garbage. So now, let's figure out yes, okay. I thought it said D for a second, and I was like, that's wrong. Okay. So how did we get from that to an alcohol? Someone said it. You protonate the oxygen, which would give you an alcohol. Perfect. I didn't see your protonation comment until after I went through my whole spiel. But thank you. All right. Could you chill for a second? So how do we feel about this one? It's a big multi-step thing. There's a lot going on. How do you feel? Feeling all right. Okay. All right is better than terrible. So we love to see it. And I can't sit like a normal human, so I'm just gonna. Cool. On to the next one. So it's another one of those wordy reactions. So what compound will be formed when HCl is added to methanol and pentanal? So pentanal means an aldehyde. One, two, three, four, five. 1, 2, 3, 4, 5. Okay, cool. So pentanal plus methanol plus aldehyde. What reaction is this one? Yes, it's the acetal-ketol reaction. And are we going to stop at the hemi, or are we going to form an acetal? We're going to form the acetal. Cool. And so when we form the acetal, we're just going to take this part, and we're going to go O and the R group, O and the R group. Off with its head. Yes, exactly. So let's look at the answer choices now. 1 chloro. 1 chloro? What the heck? Why would we do that? That's so dumb, bro. So dumb. Garbage. Blah. I can't draw an X apparently. Garbage. Okay. And then, ooh, they tricked you because they're all like di, right? And so they look kind of similar. Dihydroxy, dichloro, dimethoxy. Chloro, again, freaking dumb, ew, not chlorine. Chlorine is not attaching to this, ew. Dihydroxy would be 2 OHs, but as someone said, it will be B because it is going to be if my highlighter would work, it's going to be dimethoxy, which just means 2 ethers. Bam and bam. And let's just make sure we're correct. Ta-da, we are correct. Okay, so there's so many. Okay, let's do this one because we didn't explicitly talk about this concept. So, which of the following gem dials is expected to be the most stable? So, let's right quick draw these guys out. All right, so this is an ugly drawing, but which of these is not like the other? Okay, so someone said something about 17. So technically we're done, but I'm going to do 5 more minutes because I never finish on time. So for this one, we are looking for electron withdrawing groups because they stabilize gem diols. So now that I told you that, which one of these has a electron withdrawing group? A, yes. So CF3 is very electron withdrawing. So it's going to be the most stable gem diol since it has the most electron withdrawing group. This is just one of those things like conceptual ideas. Okay. So now I'm going to pick some chapter 17 questions. Okay, so this is a good one. So chapter 17, right? We have acid, we have an alcohol, and we have a carboxylic acid. Let's do the rosemary method. This is the leaving group. This is the nucleophile. And we cross out a hydrogen. Yes, I can go up to take a picture in just 1 second. So we're essentially redrawing this out, except we're replacing the OH with the nucleophile. And the way he tests if you really know what's going on is he puts that little O18. So the O18 is only adding where the nucleophile adds. So that being said, this and this are dumb answers. Yucky, yucky. Trash, absolutely. I agree. And this one is also trash because what the heck? Where did that even come from? That's garbage. We don't get fooled like that in this household. So now we're down to this one and this one. They both look good, except we know it has to be an O18. Therefore, A is our answer. Ta-da! And someone said, what's with the numbers? I have this gigantic packet of questions, and I go through and try to find decent ones, and sometimes it's like, it goes from like 17 to like 104. So don't worry about it. All right, so I'll leave this up for a second, and then I'm going to go... Oh, okay, so what they meant is the 18. So O18 is just an isotope of oxygen, and sorry, everything is so distracting right now. The 18 just stands for the isotope number. So instead of oxygen 16, it's oxygen 18. I wish the lights didn't hate me. All right, so let me go back up. And honestly, the only reason he does that is so he knows that you kind of know what you're talking about. You know what oxygen goes where. You're not just doing things willy-nilly. Let me turn back on. I swear I'm here. It doesn't want to turn back on. Whatever. Alrighty, so let's see if I can squeeze one more of these. Okay, this is a good one. So 3-methyl cyclopentanone. This unknown is what functional group? Ketone, cool. So I'm going to choose this to be carbon 1. So we have a ketone. And nope, I lied to you. I'm so sorry. We have a ketone. And then on carbon 3, we have a methyl. And I swear this isn't a box. There's supposed to be a point here. All right, so we're reacting that with a hydroxylamine. So a hydroxylamine gives you what product? An oxime. Perfect. So we cut this off and we add this one. And we get this ugly pentagon stays the same. And we instead have a double bond to nitrogen and OH. So which one of these answer choices looks like our oxime? Number 3, aka C, exactly. And even if you couldn't really remember what an oxime was, right? Or a hydroxylamine, you know it's not this thing, right? Like, what in the world even is that? Like, what? Ew. That's not even trash. That's just like burning garbage, right? Same with this one. What the heck even is that? What is that? You know, like, ew, what? And then we know that this is an oxime. This is a hydrazone. And this is the phenyl hydrazone. So 4 and 5 were just ugly distractors. 1, 2, and 3 all were real reactions that we did in chapter 16, but the oxime was the correct answer. So let me zoom out a little bit. All right, so now I really have to go because I have my tutoring session. But yes, I hope this was helpful. If you have any questions, let me know. I'll stick around for like another minute or so. But yeah, that's all I have for you today. I'm sending the attendance sheet one more time actually because I saw a couple people come in. So yes, that's all I have for you. Have a wonderful day. Good luck on your exam. You're going to do amazing. And the review is already uploaded. So I uploaded it earlier today. I'm going to send an announcement right now just to let people know. And then this session will be uploaded as soon as possible. Okay. You're very welcome. Bye-bye.